Hello, and welcome back. I'm very pleased with what I have to show you today as the next step in our current part of the project of generating a navigation mesh, a convex decomposition algorithm I call QuickCompose. To take a high-level look, the algorithm functions like this. Given an input polygon P, identify the next reflex vertex. While we have a reflex vertex, find the best split point on the polygon for this reflex. Using the reflex and the split vertex, divide the polygon into two subpolygons and call QuickCompose again on the new split polygon. Once the original call to QuickCompose on P returns, the navigation mesh will now contain the set of subdivided polygons. The primary inspiration and research for this comes from Mark Bayezid's decomposition and a paper from Raymond Siddell for computing trapezoidal decompositions. I will leave links for each below. There's a lot to cover, so let's look at each of the steps. The first step is to find a reflex vertex, and to do this, we walk each vertex calling isReflex, and should a positive result be found, we return the index. Determining if a vertex is a reflex vertex is done by comparing the surface normal of the polygon against the bivector created by taking the cross product of the incoming and outgoing edges. If the projection of the bivector and the surface normal is negative, then we've detected a reflex condition. This is essentially due to the polygon turning back on itself, resulting in a flipped normal. Given the reflex index returned from findNext reflex, we supply the reflex edge into the find split vertex function to return the second vertex we'll use later in the split. There's a lot of theory that's involved in the code, so I'll go over it piece by piece. To start, we create two sets for tracking the best split vertex. We'll always attempt to split a vertex in the polygon. Any vertex that is deemed visible will be stored in the visible indices. If a vertex is not visible, but the edge which the vertex is the origin of is, then we store the visible point on the edge along with the visible index information. Should all visible vertices end up being pruned or never created in the first place, the delayed edges will be used as a backup Steiner point. The reason we use a set is that we can define the less than operator like this. We always prioritize splitting along another reflex vertex should one be found. Should we need to, as a last resort, we choose the vertex with the closest distance to the original reflex vertex. By doing this, it allows the container itself to automatically track the best result for us to return. Before we begin the main processing loop, we compute what is essentially the visibility cone of the reflex vertex. This code should look pretty familiar if you've seen my GJK or QuickCall videos, which will be linked below. It's a fairly standard way of computing a side plane. The first check we make is determine if the vertex is visible, and if it is, then we'll store this vertex as a visible index. In order to perform this check, we simply use the planes generated earlier and evaluate the dot product between them and the current polygon vertex. If the dot product of the point and both planes is positive, then the vertex exists inside the visibility cone of the reflex point. Should the vertex not be visible, then we do a backup and see if the edge is at all visible. And likewise, if it is, we generate a delayed edge. Performing this check is a little more involved than if a vertex is visible. What we'll do is progressively step array and check for an intersection with the edge. During the ray cast, we're going to create two segments, one which goes along the incoming direction and one which goes along the inverse outgoing direction. We're then going to find the intersection point of the incoming and outgoing with the current edge. Should the intersection of the lines exist within the line segment, then we create the visible point at the average of the two intersection points. The intersection test is actually performed in 2D. Since all of our polygons are basically aligned to the y=1 plane, we simply use the x and z coordinates of the vertices in question. The 2D intersection test is done by using Kramer's rule to evaluate for an intersection point. If the lines are not parallel, there will be some intersection. To compute the points, the determinant of each axis is divided by the determinant of the parallelogram. We then need to ensure that this intersection point exists within the boundaries of the line segment. This is rather trivial as we just check the intersection point against the bounding rectangle of the segments. One note I would like to make is that you may generate false positives where the edge was visible at the destination vertex. However, this is a non-issue as when the vertex is evaluated, it will generate the proper visible index and be chosen in lieu of the delayed edge. After we've done our visibility checks, we need to prune our cache. Currently, we've only checked if there's visibility from the perspective of the reflex vertex. Now we need to see if the current edge obstructs any of the potential splits in the cache. We simply iterate through each cache, and if an intersection between the current edge and the potential split edge exists, then the split edge is removed from the cache. And a note I would like to make, I found this in editing, however, this code actually needs to be before we run the visibility checks, or else we're just going to end up pruning out the vertex or edge we just inserted. Once we've walked the entire polygon, we now grab the best vertex. If a vertex exists in the visible indices cache, then we simply return. Should we need to use a delayed edge, we'll likewise select the first delayed edge. However, before we return the edge index, we need to insert the visible point into the polygon. After we've inserted the point, we then use this new edge index created as the split index. Once we have both the reflex and the split vertex index, we're able to subdivide the polygon. We'll start by creating a new polygon and two new edges. The two new edges, R' and S', will be used to create the new polygon. We update the edges with the relevant information, copying over the data from the old reflex and split to R' and S' respectively. After this, the old reflex and split edges will be rerouted and linked together. This creates a twin between R' and the split edge. However, we must check if the split edge has a current twin. It is possible that this current split edge is an old R', and as a result, if the current split edge does have a old twin, then the old twin of the split edge is offloaded and paired with the new S'. After this, we create the twin between the split edge and R'. Finally, we finish off by updating all relevant pointers relating to the new split polygon. Now that we have split the polygon, we recurse into QuickCompose again, and the process repeats until no more reflex vertices are detected, at which point the polygon has been fully decomposed. To close us out for today is generating the portals that will be used later when we go on to pathfinding. I'll go more into the why with that video, but for now what we're interested in is computing the edge normals of the twin edges that we detected during the split polygon function. We very simply walk each edge of the polygon one last time, and if we detect that this edge has a twin, we compute the edge normal and a traversable boundary. We then use this information to create a portal and place it into the polygon's set of portals. Once this finishes, we have generated a fully functional navigation mesh. That is all for today. I'm very excited to get to the good stuff next, putting the NavMesh to use and showing the pathing algorithm. I hope you enjoyed this. Thank you very much for your time, and I will see you in the next one.